Passing from our decimal, if I reset it, okay, passing from our decimal, take a look, one full cycle, and then one cycle is passed, you count the second cycle, and then two cycles passed, and you count the third cycle, and so on. And then if I move this one here, take a look, what am I going to get? From 0, 0, the next one is 0, 1, then it's 1, 0, then it's 1, 1. That's exactly like in our table, and I cannot change that if I respect the counting, okay? Here I have an example. I don't want to discuss the hexadecimal, but I have an example here of the hexadecimal, and this is why here we have some letters, and this is going to be for another time. Anyway, just to make sure, now we understand.
Hi folks, see you speaking. Today we're going to take care about counting in binary. Let's start the introductory part. When you have a display, like this one here, this one has 2 digits. I said 2 digits because we deal now with the decimal base, and it's called decimal because of the old Italian 10, meaning 10, and everything is based on our fingers. So now when I count using these digits, what am I expecting? If I'm only using 1, then I'm expecting by pressing a button the display to move from the lowest symbol of the mathematical base, which is the 0, to the next one, and to the next one, and to the next one, and so on, up to 9. So up to this point, if I have 2 digits, the second one here was not doing anything. It was remaining a 0. When does it change? When a full cycle of counting is passing from 0, 1, 2, 3, up to 9, this one is going to consider, hey, one cycle passed already, so I press it once more, this one restarts to count from 0, and this one is incremented by 1. And so on. If I keep counting and I'm reaching this point where the last value of my digit is 9, is the biggest symbol in my decimal base, the second digit says, hey, you're almost counting 2 cycles. Right now you counted 2 cycles, and so on. So that's how the numbers keep increasing. So the principle of counting is actually very easy to understand, is that you can express it in 2 different ways. Either you can say the present number is the previous number plus 1, or you can also say the next number is the present number plus 1. So then, if this is 0, my lowest symbol here, and I press the button 1 time, is 0 plus 1 is a 1, and 1 plus another 1 is a 2, and so on, and that's how we keep counting. But when we change the mathematical base to the binary, and binary means only 2, we won't have the symbol 0, 1, 2, 3 up to 9. We only have 2 symbols, 0 and 1. So take a look. I'm going to use the same display, which is initially designed to be able to count up to 10 symbols, 0, 1, 2, 3, up to 9. And then, if I'm just moving the same display to another electronic diagram, like this one here, I can also see 0, 0. But when I press this button here and I only use 1 digit because it's binary now, it's going to be a binary digit because I force it to count only 0 or 1. 0 or 1. It doesn't go to 2, it doesn't go to 3, to 4, and so on. It's only counting 0 or 1. Okay? So then if you say 0, and you didn't use this one here, you're going to say 1. So this is a whole cycle 0 and 1 because the binary only has 2 symbols. And then this one is going to say, hey, you counted already 1 cycle, you restart from 0, and now you count a second cycle, but now in order to have more, I should have a third binary digits here, a third bit. I don't have it because the display is going to go too large, okay? But these ones, they become both 0 now, and it should have been a 1 here for the next one, and so on. So now I can count using the same kind of display, either in decimal if I move it over here, or I can count in binary if I move it over here. And of course, there are a couple of mathematical bases very used in computing and other electronic equipment like PLCs, but you only have to deal with 3 mathematical bases. The binary, the decimal, this is for us to understand the actual number, and the hexadecimal, which introduces some alphanumerical characters A, B, C, D, E, F, like you see it here. So this is hexadecimal, this is binary, and when I move this one back over here. Then I'm going to have my standard decimal. Okay. Now let's see how this thing is unfolding when you try to understand the counting in binary. Okay, so then I'm going to pick up a number. Let's suppose you have here a resistor. And you found under the name or the symbol of that resistor, you find a number. No other reference. If you find this number, it's going to automatically be a decimal number, and the unit is going to be by default ohms. It's always something by default. And the same happens with the numbers. Now, in the decimal, if I have the number 1000, I don't need to put the number 1000 between brackets and to write here the mathematical base as an index, because this by default can be written like this, and everybody's going to understand it's a decimal number. But if I have a binary number and I want to specify it's a binary, I have to do this. Or I can simply do that. So the base, the binary, is going to be as an index right here. Similarly, if I want to represent a hexadecimal number, I can do this, and I put as index the letter H from hexadecimal, or I can simply say H. One last example. If I represent a number in the gray code, I should have put it between brackets and to put the letter G from gray, or I can simply say, so excepting for the first in the top, which is 1000 in my decimal, the others won't be called 1000. They're going to be called 1000, 1000, or 1000 with their appropriate indexes. Let's go a bit further. Let's understand how mathematically the number 1000 is made. Let's pick up another one. 1000 is too simple. Let's pick up the number, example here. For example, for the polynomial formula. Okay. What is the polynomial formula? Is mathematically explaining how the number is made. Let's pick up the number 1237. Okay. I don't put any index, so by default it's my decimal number. In order to understand how this one is made, we're going to use something called the rank. What is the rank? Is the importance of each of these figures in the economy of the whole number. For instance, if this one was representing a number of dollars, 7 was representing the units, and 1 was representing the thousands. So the rank is always starting from the right to the left, and this is going to be the rank 0, 1, 2, and 3, and it's going to go further and further depending how big the number you want to use is. What the rank is representing, again, the rank is representing the importance of each figure inside the number, but it's actually representing the power you have to raise the mathematical base to. Example, for this one here, is going to represent the base 10 at the power 0. Here the base 10 at the power 1, base 10 at the power 2, and base 10 at the power 3. So then, how do you describe mathematically the number here? You pick up the value you find, 1, times the mathematical base raised at the power given by the rank, so 10 to the third. Then you have the second. The second is 2 times the same mathematical base at the rank 2. And then you have the next one, which is 3 times the mathematical base of the first power, and the last one is over here, 7 times the mathematical base of the 0 power. And you add them up. That's exactly the meaning of the polynomial rule or formula, because it comes from the old Greek. It says several things together. Okay? So what is 10 to the third? Is 1000. What is 10 to the second? Is 100. And you knew that because the 2 here was representing the hundreds. So 2 times 100 is 200. Plus 10 to the first power, any number at the first power is the number itself. So 3 times 10 is a 30. You knew that because 3 represented the tens. And finally, 7 was representing the units. Any number at the 0 power is 1. So here is plus 7. When you add them up all this, you get what? You get exactly 1237, which was the initial number. But this is how it's made mathematically. Once we understand this, same kind of rule or formula applies for a binary number. Let's pick up a binary number now. Another example, okay? Let's pick up a number which is 11011, okay? And I specify that's a binary number, okay? So it's not 11,011 in my decimal, it's 11011 in binary. So I'm gonna do what? I'm gonna use the rank. And the rank, going right to left, this is gonna be the least important, the next one, and the next one, and the next one, and the next one. And you do what? These numbers 0, 1, 2, 3, 4, they represent the powers of the mathematical base, because it's the binary now is going to be 2 at the 0, 2 at the first power, 2 at the second power, 2 at the third power, and 2 at the fourth power. So when you do this, you apply the same rule here. Whatever value you find is 1, is times the mathematical base at the power represented by the rank, which is 2 to the fourth. The next is 1 times mathematical base 2 at the third power. Next is 0 times mathematical base 2 at the second power. Next is 1 times mathematical base 2 at the first power. And the last one is 1 times mathematical base 2 at the 0 power. 2 at the fourth is 16, because you have to add them up. 16, okay? 2 at the third is 8. 0 times anything else is a 0. 1 times 2 at the first power is 2. And 2 at the 0 power is 1. So when you do this, and you realize this is exactly the number representing the 27 in my decimal base. So how do I write the 27 of the decimal base in binary? It's 11011. That's it. Let's pick up another one. Let's pick up the number, a longer one, 101101. And one more. Rank 0, 1, 2, 3, 4, 5, and 6. So now, the 6 here is going to represent the binary of the 6th power. I'm writing it directly to know what it is 64. Here, this one is going to represent 32, because 2 at the 5th is 32. This one is 16. This one is 8. This one is 4. This one is 2. And this one is 1. So then, is 1 times 64 plus 0 times anything else is a 0. I don't care about it anymore. The one here is times 16 plus the next one here is 8. The next one here is 0 times anything else is a 0. So I don't care about it. But this one is 1 times 2 is a 2, and plus 0 times anything else is not 0, sorry, is 1. So then I'm going to get what? I'm going to get 64 plus 16 is 80. And this is going to be 90, and you're going to get 91. So That's how the binary unfolds when you want to convert. This polynomial rule is representing, or formula is representing what? How do you convert numbers from any other mathematical base into decimal, okay? But I don't want to bother you too much with this kind of calculation. I want to show you, based on what you already know from the rank, how can you draw a table with correspondence binary to decimal very easily without calculating much, okay? So now I prepared the empty table for you here, where I only have decimal figures already in the table, and we want to figure out what are going to be the binary numbers corresponding to what we know. Obviously, if I know the numbers in my decimal 0, 1, 2, 3 up to 9, this is going to be like the first cycle here. If I'm going to do this, this is going to be my fourth cycle. If I count, there are exactly 10 symbols. This is my decimal base, okay? And what I'm going to get here, I can write nothing. I can leave it like that because I only have one figure moving. Or I can say, for the fourth cycle, I only have zeros here, everywhere, because the next figure here, I'm not actually using it. But the interesting thing, how many figures will I have? 10. And the next one I'm not using. How many times does it stay in 0? 10 times. Why 10 times? Because if I put the rank here, the rank can be figured either using letters. The first letter of the alphabet is A, so I can say here A and here B. Or I can use numbers, and when I use numbers, that's exactly what we did on the other page, and I'm going to put a rank only. This is 0 and this is 1 for my decimal. So this is going to be 10 at the 0 power, which is 1, and here 10 at the first power, which is 10. So take a look. How many times each symbol of the mathematical base, how many times does it stay here before changing? One time. 0 is one time for the first cycle. 1 is one time. 2 is one time, and so on. How many times the mathematical base allows each symbol to stay 0? 10 times, because here is 10. It's going to be easier when we pass to the binary. Let's take a look. We can put again either letters. This is what you're going to find in a lot of diagrams, or we can put the rank using numbers. So I'm going to use another color to make the distinction. 0, 1, 2, 3, 4. Okay? In a lot of electronic diagrams, the most complicated you're going to find is going to only contain 4 bits, A, B, C, D. But just to make sure everybody gets it, I'm going to put one more. Okay? So what does it mean here? It means 2 at the 0 power, 2 at the first power, 2 at the second power, 2 at the third power, 2 at the fourth power. Okay? So when we do the calculation, remember, any number at the 0 power is 1. 2 at the first is 2. Any number at the first power is the number itself. 2 at the second is 4. 2 at the third is 8. And 2 at the fourth is 16. Okay? So when a bit is found on that position, for instance, is going to be representing 2. Let's go. So here, for the first column, how many times each symbol of the binary is going to stay 0 before becoming a 1? One time, because it says here by the position and the calculation. So, one time stays 0. How many times is going to stay 1? One time. And that's exactly what we did on the other side. We're going to go at the end to check it again. If I play again with this bit, remember, this one here is a bit. This one here I circled already is a digit. Why a digit? Because it may have 10 different values. Why is it called a bit? Because it can only have 2 values. And if I play again with 1 bit, what am I going to get? 0 or 1? And if I do this again, 0 or 1. So take a look how easy it is. It's because of the rank here. The rank was 0. The 0 was representing the binary 2 at the 0 power, which is a 1. This calculation tells me how many times I'm going to have a 0 on the first column before changing to 1. One time.
How many times I'm going to have a 1? One time also, because the two symbols are having the same priority in the base. So I'm going to put here 0, 1, 0, 1, 0, 1. It doesn't matter how long my table is. I'm going to get only 0 1s everywhere. So I'm going to take my time to fill this 0, 1, 0, 1 for as long as I have my table to fill, okay? Just to show you that if I only have to play with one bit, the bit can only have two values. Now what am I going to get on the next column here? Because I have the calculation, the rank is 1, 2 of the first power is 2. The 0 is going to stay 2 times here before becoming a 1. So I'm going to have 0, 0. And then I'm going to have 1, 1. And then I'm going to have 0, 0. And then 1, 1. Because for all these columns here, I know how many times the first symbol of the base remains. 2 times. The first symbol of the base is 0. The second symbol of the base is 1. So if I use them again, they are going to do the same thing. So I'm just going to fill the table. 0, 0, and 1, 1. And 0, 0, and 1, 1. And so on until I reach the end of my table like this. What am I going to find on the next column? I'm going to find the 0 4 times before changing it to 1. So take a look. 1, 2, 3, 4. And then how many times did I get a 1? Also 4 times. 1, 1, 1, and 1. And then if I use them again, it's going to be the same story. 4 times a 0 and 4 times a 1. 4 times a 0, 4 times a 1. I'm taking my time to do it. 4 times a 0 and 4 times a 1. Now I'm only having 2 zeros because my table stops here. I didn't want to make it longer than 1 page. Okay. Next column. If I want to fill binary values on the next, how many times I'm going to get 0 before changing it to 1? 8 times. So 1, 2, 3, 4, 5, 6, 7, 8 times a 0. How many times is going to be 1 present here on my table? 8 times. And then if I use them again, 8 times a 0. And guess what? 8 times a 1. Just to fill my table, I'm going to put 2 more zeros, okay? Because my table should go lower. And if I ever use the 5th, guess what? I'm going to have 16 zeros. I don't fill them yet because I just want to figure out what happens up to now, okay? Let's pick up a decimal number from here. Let's pick up this one, 11 in my decimal. I'm going to pick up what's the equivalent binary number I just built right here without doing any calculation actually. I just count it. 1 time, 2 times, 4 times, 8 times. So again, I pick up the number 11. What am I going to get? 1, 0, 1, 1. I put it here. 1, 0, 1, 1 in binary. Remember, I put the rank. The rank is, let's put it like that, 0, 1, 2, and 3. This is representing 2 of the third, 2 of the second, 2 of the first, and 2 of the 0 power, okay? Well, what is 2 of the third? It's 8. 2 of the second is 4. This is 2, and this is 1. So then, I'm going to hit here 1 times 8 is 8. Plus, here I have a 0. I don't care about it. I have here a 1, and 1 is times 2 of the first, which is 2. And the last one is 1 times 2 of the 0, which is 1. So I'm going to get 8 plus 2 plus 1. And that's 11 in my decimal. And that's what I said. When I look here, 1, 0, 1, 1, it's 11. So you see, I can check any number on that table here. Let's pick up another one. Let's pick up the number. If I fill the next column now to make it more complicated, I said on the last column, if I had it, I had 16 times a 0. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times a 0, and 16 times a 1.
4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm going to put 2 more zeros to fill the table. So I'm going to pick up another one. Let's pick up the number 11010. 11010. Okay? Rank. The rank is, as it was before, 0, 1, 2, 3, and 4. And for this one, I'm writing here in the top directly the calculation of the binary of the power given by the rank. 16, 8, 4, 2, 1. When I find the 1, I write the value here, like 16. When I find the 1, I write the value here, 8. When I find 0, I pass over it. When I find 1, I write the value here. When I find 0, I don't write anything. So this is going to be 26, okay? So if you take a look, this is the number in my decimal, and the number was 11010. I look for it here, where it is, 11010. Take a look, it's 26, okay? So for any of these binary numbers we just built using a simple, very simple method, we're going to find the decimal figure right away. I don't want to discuss today the hexadecimal because we make it too complicated. I just want to focus on the binary because that's essential to understand. How can you build a table any big you want? If you had another value here, it would have been the rank 5. So 2 of the 5th was 32, okay? So the first, how many times it was staying in 0 before becoming a 1? 32 times. And then 32 times in 1. And you can extend this table to make it any big you want, okay? And then if you want to pick up any number from here, let's say randomly, you can check it. Now, one last thing for this table is, depending on how many bits you use, what is going to be the biggest number you can get? Let's say here, if you pick up 2 bits. With 2 bits, I'm writing here number of combinations. How many ways are there to combine the first 2 bits? 1, 2, 3, 4 ways. And you knew that already because when we studied all the logic gates together, we put the values of the inputs, the 2 inputs, 0, 0, 0, 1, 1, 0, 1, 1. Now you know why. Because they were coming in the ascending order from 0 to the maximum. Okay? And if you're using it again, the 2 bits, take a look what you get. The same 4 combinations are repeating themselves. And if you use them again, they repeat themselves and so on. So you have all these 4 combinations repeated all over again. And the number of combination is the mathematical base. So this is binary. The power given by how many figures you used, how many bits? 2. 2 at the second power is 4. So you find how many ways you have to combine these inputs. 4 ways. Example, if you have 3. If you have 3 figures, you are going to find out that you are going to get up to here. It's 4 times a 0, 4 times a 1. So this one is going to repeat all over again. Here is going to be the same, and so on. So on 3, number of combinations is 2 at the third, because it's the binary of the power given by how many figures you used. 3 figures in this situation is going to be 8. So this is the binary. And this is the power given by how many bits. So this is why you have 8 combinations if you use 3 bits. And if you use 4 bits, guess what? Number of combinations is going to be 2 to the 4th power, 16. So if you have 4 wires to combine together, how many ways are there to combine 4 wires or 4 switches? 16 different ways. Okay? Not 12, not 13, not 15, 16. And now, the biggest number. The biggest number
is the number of combinations minus 1. Why is this? Because the first combination is a 0. So example, if you only have 2 bits, what is the biggest number you have? 1, 1. 1, 1 means what? Is 3 in my decimal. So if it is 3 in my decimal, the number of combinations was 4. 4 minus 1 is 3. If you have 3 bits, with 3 bits, the biggest number we get is here, when all values are filled by ones, is 1, 1, 1. 1, 1, 1 is representing 7. But the number of combination with 3 bits is 2 to the 3rd power 8. 8 minus 1 is 7. On 4 bits, it's going to be this one here, the biggest number. The biggest number is all the values are filled by ones. So what is this? On 4 bits, you have 2 to the 4th power, which is 16, minus 1. What is the biggest number you get? It's 15. Why is 15 again? Because you have to start from 0. You don't start from 1. So this is why if you are starting from 1, the last one would have been 16. But you start from 0 because that's the first symbol of the decimal. So the last one you get is 15. Eventually, guess what? If you have 5 values, 5 values are right here, 1, 1, 1, 1, 1. And this is 2 to the 5th is 32, minus 1 is 31. So here, that's the formula to understand what is the biggest number we can get depending on how many bits you use, okay? So if we go back one more time to the digits to see them, here they are, okay? So here, passing from our decimal, if I reset it, okay? Passing from our decimal, take a look, 1 full cycle, and then 1 cycle is passed, you count a 2nd cycle, and then 2 cycles passed, and you count the 3rd cycle, and so on. And then if I move this one here, take a look, what am I gonna get? From 0, 0, the next one is 0, 1, then it's 1, 0, then it's 1, 1. That's exactly like in our table, and I cannot change that if I respect the counting, okay? Here I have an example. I don't want to discuss the hexadecimal, but I have an example here of the hexadecimal, and this is why here we have some letters, and this is gonna be for another time. Anyway, just to make sure, now we understand at least the basics about how to count in binary. So guess what? The next time we're going to build a counter doing this for us. Thank you very much for watching. See you next time. Bye-bye.